Okay, we stopped here last time. We were talking about the rolling process. Already we started last time. This is chapter 15, bulk metal deformation. The first process in the bulk metal deformation is the rolling. Already we started last time. We are in a rolling. So today talk about the flat rolling and its analysis. Analysis of the rolling. So this is a rolling process. Rolling is squeezing the workpiece material between two rotating rollers, one rotating up, one rotating down, and you squeeze the material. Squeeze the material, you're feeding the material, and you're squeezing the material, applying compression test here. Then you reduce the as you can see here the section, the thickness. You reduce the thickness here. So this is the rolling process. Here in analysis, we remove the upper roller. We remove the upper roller. We only keep the lower roller, and the upper roller is removed here. So you can see, right? This is a workpiece. This is the roller. This is a workpiece. This is a WO. WO mean width. TO means thickness. VO means speed, initial speed. So O meaning initial speed, initial width, initial thickness, and WF is a final width, TF is a final thickness, VF is a final speed. This is a roller. This is a roller. VR is the rotating speed of the roller. Speed of the roller. VR is the speed of the roller. This is the terminology here you can see. D is the roller diameter. D is the roll diameter. N is the RPM of the roller. L is the contact length here. This is the L, contact length between roller and workpiece. L, this is L, contact length between roller and workpiece. R is the radius of the roll. We have whatever we call is draft and reduction. Draft is the TO minus TF. TO minus TF. Because TO bigger, you start with a bigger thickness. This is the TO, this is the TF. So TO minus TF is a draft. Right? Reduction is a D divided by TO, which is a draft divided by the TO. Draft divided by TO is a reduction, right? Okay, so this is information about this one. In a rolling process, please listen to me carefully. In a rolling process, volume is constant. Yes. All material deformation process, volume is constant. You start with certain volume, you end with the same volume. No cutting. We are not removing any material here. We are not removing any material. So volume is constant. You start with certain volume material. When you finish, you get same volume. You deform the material. Dimension will change, I agree, but the volume is constant because we're not going to remove any part of material. So TOWOLO, L is the initial length of the sheet that you start with. The sheet that you start with. TOWO is the cross section multiplied by LO is the length of the sheet equal to TF multiplied by WF multiplied by LF. The sheet after you finish. You start with certain dimension, you end with different dimension, but volume is constant. Also same here, in the same way, you can say the volume flow rate is constant. Volume flow rate, which is a VOA. Cubic, this is a cubic, you can see that, we can see here, cubic millimeter. Volume is what? Cubic, for example, cubic millimeter. This is a flow rate, right? So this is a volume, sorry. Volume flow rate here, if you talk about volume flow rate, what is a volume flow rate? Volume flow rate is cubic millimeter per minute. Cubic millimeter per minute is the volume flow rate. Volume flow rate is equal to VAO equal to VFAF. VO is the initial speed. AO is initial cross section, which is equal to TOW. AO equal to TOW. This is the TOW. This is the W. Let me write. This is the W. Width. which is the WO. Let me say this is WO, and this one is the TO. So you can see that TOWO, TOWO, which is A, then A, which is TOWO multiplied by VO. VO is initial speed, starting speed or initial speed, equal to VF AF. VF is final speed multiplied by AF, which is the final area, which is T final multiplied by W final, right? Then in this case, a volume flow rate is also constant. Not only volume is constant, and volume flow rate is constant. Okay, so volume flow rate is constant. What is the issue? You can see that, please give me your attention. If volume flow rate is constant, then you can see that AO, this is the AO, this is the AF. You can see that what is the relation between AO and AF? AO is bigger. The area, initial cross-section area bigger than final cross-section area. Then as well as AF is smaller than AO, AF smaller than AO, AF is here, right? Then you can see that AF is smaller than, is low, AF is low. AF is low, and AO is high. As AO, can you see that? As AO is bigger and AF is smaller, then what about the VO and VF? Then VF must be bigger because this one constant. This value is constant. VA is constant. Then VF AF equal to VO AO. Then this one is constant, right? If AF is smaller, then VF must be bigger. Then VF to compensate, right? Then VF must be bigger than VO. Then VF must be bigger than VO. No way. Then VF must be bigger than. Then this is VF higher than VO. Exit speed must be higher than initial speed. So entrance speed is low, exit speed is higher. Why? Because the flow rate is constant. The VO AO equal to VF AF, and AF here, as you can see, AF here smaller than, AF here smaller than, then VF must be bigger than VO. So VF must be bigger than VO. Then you can see that, please give me your attention, guys. Please give me your attention here. Then if you hear, this is a starting point. This is a starting point, right? This is a starting point. This is the exit point. So this is the exit point. So exit point meaning VF here. This is a VF here. Let me say this is a VF here. This is a VF at exit point, and this is a VO at starting point. So at starting point, this is a VO. At starting point, this is a VO, right? This at exit point, this is a VF. At starting point, at VO. Exit point at VF, right? Then the speed increase. Speed here increase during the rolling process from here to here. During the rolling process from here to here, speed increase, change from VO to VF, right? Let me just show in a bigger. So this is a bigger photo. Then as I told you, this is a starting point here. This is a starting point. Then rolling start here, rolling end here, finish. So rolling start at this point, rolling finish at this point. And then as I told you here, this is the starting point, right? Starting point here, enter at VO and exit at VF. Please guys give me your attention, huh? Please give me your attention. Then start at VO here. This is the VO, this is the VF. VO smaller than VF. VF is faster. Then you expect that the speed will increase from VO to VF. However, please realize that this is a roller, right? Roller rotating at constant speed. Roller rotating at constant speed, which is a VR. Let me say this is a VR. Constant speed. All time constant speed VR, right? All time constant speed VR. Then roller rotating at constant speed, which is a VR, right? You agree? So roller here rotating at VR. Let me write. This is a VR. VR, what is a VR? VR meaning V roller. VR meaning V roller, speed of the roller, equal to what? By dn. By dn, or this is the omega r. Omega r. V here equal to omega r. Omega is the rotational speed, r is the radius, which is equal to by dn. Then omega, then Vr equal to by dn. N, what is the N? Revolution speed of the roller. 10 revolution per minute, 20 revolution, 100 revolution per minute. This is the R by dn. By dn is the Vr. So Vr is constant, right? Where is the Vr? Actually, Vr is in between VO and VF. Something here in between. So this is a VR. So VR is something between VO and VF. So this is the VO, this is F. I mean, you can see that the speed here when the rolling process start here, material will enter at VO and will exit at VR. Actually, roller is a drive. Roller is a drive. Roller is a drive. What does that mean? Meaning roller is rotating like this. Drive the motion. Roller rotating the drive the motion. Who is the main drive to feeding this one? Feeding at VO and exit at VF and VR in something in between. So VR here, so speed will increase here. So this is a workpiece and this is a roller. Actually, they are not same. They are two different parts. This is a roller and this is a workpiece. In the surface, in the workpiece surface, the VO exit enter as a VO, exit at VF, and speed here increase until reach VF, and here at this point become VR. So at this point, we have constant speed. V, the speed of the workpiece is a VR, and the speed of the roller is VR, right? Then here both have VR. If you look to here from beginning, you can see the workpiece speed is VO. Roller speed is a VR. They are in contact, but there are a different speed at this point. Here also you can see that the speed of the roller at this point on the roller VR, but in the workpiece is VF. They are in contact. However, in this point, at this point, speed of the workpiece is a VR, speed of the roller VR, meaning constant. We call it is a natural point or no slip point. This point is a no slip point. Before that, speed of the roller is higher than the speed of the workpiece. After this point, speed of the workpiece is higher than the speed of the roller. Then if the speed of the workpiece and the roller are different, then we have slipping here and we have slipping here. Roller slip on a workpiece and workpiece here slip on the roller. slip mean يعني بيتزحلق على الرولر او يعني بيتحرك. There are a relative motion between this one. Here relative motion is zero. At this point relative motion is zero because at this point the speed of the workpiece is VR, speed of the roller also VR. As long as there are a different speed between the workpiece surface and roller surface, then there are a slipping and there are a friction here. There are a friction here. You can see that there are a friction here because the roller try to push, try to feed the workpiece to flow inside. This direction, the friction in this direction is a clockwise direction at this half. But later, after no slip point, you can see that friction is opposite. Why? Because the speed of the workpiece is faster than the speed of the roller, then you can see that the friction is opposite. Then the friction in this direction feed forward to feeding this one to move. In the other half, the friction is the opposite direction. This is the amount of slip between the roller. We call S equal to Vf minus Vr divided by Vr. This is the slip value between this one. We call it the forward slip. When you move here, you can find that friction F1, friction F2. F1 trying to, in this direction, trying to feed, pushing the workpiece to move inside. Friction F2 is against the motion because here the speed of the workpiece is higher than the speed of the roller. But definitely F1 bigger than F2. If F2 bigger than F1, no motion. It will not move, right? Then must be F1 bigger than F2. Then always friction in this half bigger than the friction is the opposite direction. Then draft equal to TO minus TF. TO minus TF. This is the draft. Or TO minus TF. This is the draft. And then limiting draft, maximum draft we can achieve in one cycle. Maximum draft we can achieve in one cycle equal to mu square R. Mu is a coefficient of friction because we said that friction drives the motion. Always friction drives the motion. Friction here drives the motion. You see, then the maximum draft, maximum reduction, as you can see here between TO and TF, is equal to, can be obtained as mu square R. Mu square coefficient of friction between the roller and surface. R is the radius of the roll. Radius of the roll. The maximum draft, this is the maximum draft can be achieved in one cycle. If the draft, if you try to make draft bigger than this one, then roller will slip, will not achieve the rolling process. It is not possible. Then the roll will slip above the maximum. If TO minus TF bigger than the maximum, then the maximum achieved by mu square. Yeah, I mean, if you know the coefficient of friction and R, you multiply, you get this is the maximum draft. Then the maximum what you can achieve TO minus TF is a Dmax. If you try to achieve bigger than the maximum, I mean TO minus TF bigger than the maximum, this roll will slip and will not achieve the rolling process. So maximum draft can be achieved is equal to mu square R, right? Then mu is a coefficient of friction. You can see that, you realize that coefficient of friction is very important. In a rolling, coefficient of friction is very important because friction is driving the motion, feeding the workpiece to move inside, to squeeze, then you move inside to do the rolling process. Then the coefficient of friction between work surface and the roller. It depends on the working material and depends on working temperature. It depends on the working material and it depends on temperature, right? In cold working, it is around 0.1. Mu is around 0.1. In cold working, mu around 0.1. In warm working, usually 0.2 because temperature increase. In hot working, it is usually 0.4. You will ask me why? Why when temperature increase, coefficient of friction is a change? In cold working 0.1, in warm working 0.2, in hot working 0.4. Why? Why it is like this? Why different temperature leading to different coefficient of friction? Actually, because this is a surface, the workpiece surface and roller. This is a roller and workpiece surface, right? Whenever you apply pressure, something like this. This is in cold working. This in cold working. In hot working, material becomes soft, become softer. Material becomes softer mean it deform more. So in cold working, certain deformation happen in this way. But in warm working, more deformation happen and more contact between the surface happen, leading to higher coefficient of friction. In hot working, more and more deformation and material penetrate in each other more, leading to higher coefficient of friction. You told me you will say that perfect. More coefficient of friction is better because the maximum draft equal to mu square R, meaning that maximum draft we can achieve is higher in case of higher coefficient of friction. Meaning when a higher temperature, when we have higher temperature, higher maximum possible draft can be achieved. Yes, it is. Actually, it is correct. However, in hot working, this one becomes severe. In hot working, this one becomes severe because you see that in hot working or hot rolling, it is 0.4. Sometime if temperature we reach whatever we call is sticking, and when this is sticking, when we have a higher pressure, this coefficient of friction increase sometime to 0.7. In hot working, increase sometime to 0.7. When it is highly increased, there are a severe damage happen in a workpiece. Why severe damage? Let me go back to the previous slide. Okay, you can see that. Let me go back one more. Here, we said there are a relative motion here, and there are a relative motion here. There are a slipping here. There are a slipping here. Is the coefficient of friction increased to 0.7? Then there will no way. This surface, these two surfaces on each other will not be able to slip anymore. Why? Because it's sticking. Because the friction here very high. Then this one, the roller will push the workpiece surface to move in the same speed, which is a VR. But it is not possible because here we have VO and we have VF here. Then what will happen? You can see that the internal layer, the layer which is the next layer, will slip on then the internal layer will slip. Slipping happen here in the internal layer, leading to damage because here stacking happens in the surface of the workpiece and surface of the roller will move together in the same speed, which is the VR. Then slipping on the layers as the workpiece layer, slipping happen here, damaging the surface and leading to crack below the surface. So also very high friction is not good. So when sticking happen, the coefficient of friction increase to 0.7 or sticking happen in a hot working. The consequence of sticking is that the surface layer of the work are restricted. Surface layer of the workpiece are restricted to move at same speed as the roller speed, which is the VR. And this is not possible because there are a different speed. However, then this one will happen, but below surface will not follow. Then below the surface, deformation is more severe. Slipping on the material layer happen in order to allow passing the piece through the roll gap. This one leading to severe damage below the surface of the workpiece. So also friction is okay. Higher friction is fine, but very high friction is bad actually. So 0.1, 0.2 is reasonable, 0.3 is okay, 0.4 is high actually. But if you reach 0.7, then severe damage will happen in the rolling process. We should not allow the friction to increase up to this level, right? Then you can see that here to see you, this is the no slip point. Here, this is whatever we call no slip point. This is whatever we call no slip point. No slip point, you know that. VR. The speed of the roller, VR, speed of the workpiece, VR. At this point, we call it is a no slip point or natural point. This no slip point, it depends on the mu, coefficient of friction. Higher coefficient of friction, smaller coefficient of friction. The location of this point is different with the friction. So you can see that if friction coefficient of friction is 0.4, if coefficient friction is 0.3, if coefficient of friction mu equal to 0.2, if less, smaller, then smaller coefficient of friction. When you have a smaller coefficient of friction, this point will become closer to the exit. When you have a higher coefficient of friction, this point will become closer to the entry, move to very close to the entry. If the coefficient of friction is very small, then slipping will happen. If it is small and here, then slipping will happen. The roller will not be able to push this one to feed. Then friction is very important, as you can see. So mu here, locating this position or the point is located based on the coefficient of friction. Right. Okay, when you come to the force, force is equal to rolling force. Rolling force is coming from the pressure. There are a pressure. Where is this pressure? Please give me your attention, guys. Please give me your attention. Okay. There are a pressure. Where is this pressure? Here. Pressure. There are a pressure from the roller on a workpiece. You understand? There are a pressure here. There are a pressure from the from the roller on a work surface. This pressure, why we have pressure here? This pressure coming to compress. We apply compression test here to reduce the cross section. Then simply pressure multiplied by the area. Then pressure multiplied by the area is the force. Where is the area? Area is here. So you can see that this is the area, right? As you can see here. So this is the area, right? Let me just make it in smaller value here. This is the area. Let me tell you, this is like this. Is if you do like this, then this is the area, right? This is the acting area. This is the roller, right? So this is the area, pressure on this area. If you simply multiply the pressure on the area, BA equal to F. This is the area. Can you see that? This is the one. This is the area here. So this is the area. Then BA equal to F. Then to get the BA, this is the area, as I told you. This is the area. So this is the angle. So this is the area here. This is the width. This is the width, right? So this is the width. If you just make this one like this, so this is the width of the workpiece. This is the width of the workpiece. So this is the width of the workpiece. So area here, L multiplied by W. Actually, this pressure is distributed, not simply like this. Then to calculate, we need to take element. This is the element, small element. So this element, as you can see here, will take element. We do integration from 0 to L. To get the force, exact value of the force, we do integration from 0 to L. This element will move from 0 to L. This element, as you can see, the dimension here is a DL. The dimension here is the DL. DL meaning small part of L. DL multiplied by W. Then DL multiplied by W give you the area, the projection area for this element. So DL multiplied by W is the area multiplied by the pressure, small pressure applied here. This is the small pressure applied here. Then you can see that the pressure multiplied by the area, which is DL multiplied by W. DL multiplied by W. This is the small area of the element. We take element here. This is a small area, so small area equal to dl multiplied by w. Then pressure here, pressure multiplied by w is constant, no change, multiplied by dl, and then we do integration from 0 to L to cover all the areas, then you get the force. When they look to what happening from 0 to L, they find that this is the L. They find that the pressure increase up to no slip point, and then pressure decrease. Then they realize that it is not one part, it is two parts. From 0 to no slip point is one area, and from no slip point to the end is, or to the exit, is another area. Then actually force here must be divided in two sections. This is one section, this is another section. The first section is the B R d theta. This dl here equal to R d phi. Phi is the angle of the element. This is a small angle here, we call it phi or d phi. Then R is the radius of the roll. So R d phi is actually is the dl. Then pressure R d phi, which is the dl multiplied by w is constant, and the dl here equal to R d phi, because here we're going to start from 0 to this angle, and from this angle to the end. Then B R d phi, dl equal to R d phi here. Let me say dl here, dl equal to dl here equal to R d phi. So dl here, this is the dl, right? Dl, this is the dl equal to radius multiplied by d phi. So R d phi is in pressure. R d phi, this is the first from 0 to phi n. Phi n is the angle up to the angle up to the no slip point. And then next section from phi n to alpha, from phi n to alpha to n to the exit B R d phi w also. W can be taken as a common here. So this is a force. If you do this integration, you can obtain the force. However, this is really very difficult to achieve. This is the exact solution. This is the exact solution. This is the exact solution. Is to do like this. This is the exact solution. However, they find this is very difficult. To do this integration process, very difficult. They say that, okay, force equal to pressure multiplied by L multiplied by W, which is the pressure area under the curve. The force is the area under curve, which is the pressure, and L and W. They said that, okay, we can make average. Instead of something like this, then make it average and make it easy. Then here, this is a B average. So this is a B average pressure from beginning to the end. And then we have a certain shape. Then F equal to LWB average. This is the B average. Then L, this is the L. W is the area. And multiply B average, just simply make it easy. Then you can say that it is L, which is a contact length multiplied by W multiplied by the pressure. Understand? So it is here. This is the area. Let me say this is the area. If you extend here like this, sorry. If you extend here like this. If you extend here like this. If you extend here like this. Right? In very simple ways, he said, let's make it easy. Let's make it easy. Don't make it difficult for people in the industry, because every time to do integration, it's big headache. So this is the area actually. This is the area. Pressure applied on this area. Then a force equal to average pressure. Let's say it is average pressure. Here actually it is pressure increase like this and decrease like this. This is actual. But this is that, okay, just simply make it average pressure. Just give me, Muhammad, just give me a minute to finish, and then you ask me. Then they said that, okay, this is the area in very simple way. Pressure, average pressure multiplied by L multiplied by W. L is the contact length and W is the weight of the workpiece. In this way, they said that, okay, let's agree that LWB average is force. L here is a contact length. L here is a contact length, can be obtained as square root RD. R is a radius of the workpiece, radius of the roller, and D is draft. D is the draft, which is equal to TO minus TF. Okay, so this is equation. Yes, Muhammad, I'm listening.
Doctor, can you please repeat again, how will this integration come in the final exam, for example? الانتجريشن صداع صراحة.
ما احنا مش هنعمل الانتجريشن، انا بوريكم الاكزاكت سوليوشن، ده الاكزاكت سوليوشن. لكن احنا سمبليفايد، يعني هم سمبليفايد البروبلم، بقت بمنتهى البساطه الايكويشن اللي احنا نستخدمها الفورس ايكوال تو ال دبليو بي افريج. ال is a contact length. This is the mean area. LW meaning area. Pressure العمليه بمنتهى البساطه pressure multiplied by the area. This is the area. This is the area. Let me say this is the area. Right? Then this is the area. Pressure multiplied by area get force. So this is the area. LW is the area. What area? Area that pressure applied on. Where is this area? This is the area here. Let me show you. This is the area. Did you get it?
Yes, thank you.
This is the area. So area here equal to what? Area here equal to L contact length. This is the contact length multiplied by W is the width of the workpiece. So contact length multiplied by W. This is the area multiplied the B average. Then this is the force. This is the force applied or force needed to do the rolling process. In very simple way, right? Let me go to the next slide. Just give me a minute to go to the next slide. Then F equal to LWB average, right here. Then L equal to B average LW. Actually, this B average, what is the B average? Average pressure applied on the workpiece. Average pressure applied on the workpiece is the stress. The pressure here is like stress applied to flow the material. You agree with me? Then average pressure here, and if you said B average here is the stress actually, is a flow stress. Average pressure is the flow stress applied to flow the material, to deform the material. It's very similar to what happening here in the stress strain diagram. This is a true stress, true strain diagram. It's very similar to happening here. Stress increase up to certain level, flow the material. Then average pressure is very similar to the average stress. It is considered as average pressure is considered as average flow stress required to flow the material. Then you can say that the force equal to LW Y bar flow. Then force, the rolling force equal to LW multiplied by Y bar flow. Because in all cases this pressure will flow the material. This pressure will flow the material when reach to the Y bar flow of the material. This pressure, needed pressure to deform the material is equivalent to Y bar flow of the material. When you reach Y bar flow of the material, when you increase the pressure, when you reach to Y bar flow, material will flow. Then average pressure is the average flow stress. Actually, is the average flow stress of the material. Then this is the equation, rolling equation. Then Y bar flow equal to, you can see that Y bar flow equal, as we previously described, equal to K epsilon N divided by N plus 1. Epsilon equal to ln TO divided by TF. This is the TO and this is the TF. L equal to square root RD. D equal to TO minus TF. This is the equation that we're going to use in a rolling process. Okay, so this is a force. This is a force value, which is pressure multiplied by area. So a torque required, torque needed. This is the center of rotation of the roller. Center of rotation of the roller, right? This is the center of rotation of the roller, and this is a force. Then the torque required to do the process equal to 0.5 FL. 0.5 is the arm. Because the torque equal, if you look, this is a force. Torque equal to what? Equal to FR. What is the R? Radius. is the torque arm. This is the torque arm. This is the force. They find that it is 0.5 L. The torque arm here, this is the value, is equal to 0.5 L. This torque equal to 0.5 LF. 0.5 LF. This is the torque required to do the deformation process in rolling. Then power equal to T omega. Power equal, the power needed equal to torque multiplied by omega, which is 0.5 FL. This is the torque multiplied omega 2 by N. Then you multiply, then 2 go with 0.5, then FLN. Then power equal to FLN for one roller. Per roll, power equal to by FLN. This is the power for one roller. For two roller multiplied by 2. The total power is upper roller and lower roller. By roll, one roll. This is the power per roll equal to by FLN. For two roll, you multiply by 2. Then the power equal to by F per Newton, L meter in the RPM divided by 60,000. 60,000 because 60 to make it hour. This is a kilo, to make it second, sorry. This is called kilowatt. What is it? To make what, you have to change the dimension. So 60 means 60 multiplied by 1,000. 1,000 to make kilo. 1,000 here we divided by 1,000 to make kilowatt. What here you need second, not minute. So you divide by 60 to get second. So kilowatt. This is a kilowatt. Just forget about the horsepower. We're not using horsepower. But just only we use a unit. I mean the SI unit. Then this is the equation. Actually, this is a power equation by FLN. This is a power equation. Okay, let's take an example. Let's read it together and try to understand and solve together. Please give me your attention, guys. 300 millimeter wide strap. Wide means the width is 300 millimeter, 25 millimeter thick. Here is TO equal to 25 millimeters through is fed through a roll mill with the two powered roll. Two powered roll meaning one up, one down, right? This is the two powered roll up and down. Each radius 250 millimeters. This is the radius of the roll, 250 millimeter. The work thickness is to be reduced to 22. I mean that it is 25, start at 25 and exit at 22 millimeters. Then here draft equal to what? Draft equal to here equal to 25 minus 22 meaning 3 millimeters. So we have here, we're going to make draft 3 millimeter in this process. In one pass meaning one cycle. Is you will ask me it is two, but maybe I will discuss this one later, right? In one pass meaning in one process, draft is 3 millimeter in one pass at roll speed 50 revolution per minute. 50 here RPM is 50 revolution per minute for the roll. Work material has flow curve. K is given. Here, this is a flow curve information. This is K is given. For the flow curve, K is given and N is given. K and N of the flow curve are given. And the coefficient of friction between, this is the mu between the roll and work piece is 0.12. This is mu. Determine if the friction, the question here, determine if the friction between here is sufficient to permit the rolling operation or not. And if okay, calculate the force and torque and horsepower. Right. So first the question, is it okay? Then you have to calculate the maximum draft. Maximum draft equal to mu square R. Mu square R then 3.6. So maximum draft is 3.6. Draft you're going to perform is 3. The one you're going to perform is 3. But maximum you cannot exceed 3.6. Then as long as the draft that you're going to achieve less than the maximum draft you can achieve, then okay. Then the first question, is the friction okay enough to do the process? Yes, it is. You understand, guys? Okay, if we find that, for example, maximum draft is 2.5 or 2 millimeter and you would like to achieve 3, is it possible? No. These must not achieve or must exceed the maximum draft. So in this case, what to do? How to solve the problem? In this case, either to change the radius, increase the radius of the roll, to increase, you have to increase the maximum draft, increasing friction or increasing radius. If no way we cannot change maximum draft, what to do? Make 2 cycles. If you would like to achieve, for example, maximum draft is 2, and you would like to achieve 3, then make it 1.5 millimeter and 1.5 millimeter. In 2 pass, one pass 1.5 millimeter, another pass 1.5 millimeter, then you can solve the problem. Anyway, here is okay. Then calculate the force, torque, and horsepower. Force, put the equation. LWY bar flow. L is square root RD. R is given, and D is given. Then you calculate, this is the D is the draft, which is 3 millimeter, and R 250. Then you calculate L, this is L. W is given already, no problem. Y bar flow, we don't know. Then Y bar flow, put the equation. Y bar flow equal to K epsilon N divided by N plus 1. Epsilon equal to TO divided ln TO divided by TF. This is the TO divided by F. This is the epsilon. Then you apply K and N are given. Then you apply get Y flow. Then Y flow is okay. L okay. W is given. Then you can calculate the force. Then go to next slide. Then force can be calculated. This is the force. We need to obtain torque. Torque equal to 0.5 FL. F is no. And L already we obtained in the last slide. Then you can 0.5 FL. Then you can obtain. And then power per roll is by FLN. But here he would like to have the total power. Total power, then you have to multiply by 2. Then 2 by FLN. Then 2 by FLN. Then you can obtain the total power. So this is the total power. You can also obtain horsepower if needed, but usually you will ask about the SI unit, right? Ways to reduce the force and the power. He said that this power is probably high. How to reduce the power? How to reduce the force and the power? This is the equation. Put the power equation by FLN. Then FLN. To reduce the power, you can reduce F or L or N or all of them, right? One by one. Right. So N, you can reduce the N, RPM. To reduce the power, you can reduce N, RPM. You can reduce L contact length, which is the L here. Let me say L, this is L is the contact length. You can reduce L. This is square RD, so RD meaning you can reduce R and D. R and D. R is the radius of the roll, D is the draft. Or F equal to Y bar flow LW. L is L and Y bar flow here to reduce F Y bar flow, meaning K and N and epsilon. You reduce K and N and epsilon. So using hot rolling rather than cold rolling, meaning K and N. You reduce K and N. If you reduce K and N, you reduce Y, you reduce the force, you reduce the power. So K and N mean make a material more soft. To reduce K and N meaning material more soft, meaning you move to hot rolling or warm rolling rather than cold rolling. Reduce the draft here, as you know that you reduce the draft. This is the draft here because L equal to square root RD, then RD reduce the draft, meaning instead of 3 millimeter, make it 2 or make it 1. Radius, reduce the radius, or the reducing N RPM of the roller. This is the way how to reduce the power and force, right? Another example in the rolling a flat plate sheet, maximum draft is limited by the amount of friction. Actually, this one is very similar to the previous one. Exactly same. So let me just skip, move forward. This is the next one. This is a little bit different idea here. A plate is 250 millimeter wide. Wide is given, 25 millimeter thickness is produced in a single pass. In 2 high rolling, this is a 2 high rolling mill. Thickness 20 increase, reduce to 20, 25 and reduce to 20. The roll speed 30 meter per minute. Roll speed 30 meter per minute, which is the V. V equal to by dn, right? This is the V, speed, roll speed V equal to 30, not RPM, but V, then equal to by dn. The work material strength K is given and N given. The coefficient of friction of the roll workpiece is 0.2. Determine average roll force for minimum possible roll radius. What is that? Minimum possible roll radius. Minimum, the word minimum possible roll radius, it means that a maximum draft is equal to the draft in one cycle. I mean, in one cycle, our draft, we will maintain our draft to the maximum possible draft. It means that you calculate mu square r and we will fix our draft to mu square r. Then in this case, first step here, mu and r given, then you calculate the draft, maximum draft. Maximum draft is our draft. Then from here, you can obtain the draft value, then you can obtain L, then you can obtain the corresponding force. So to calculate L, you need to know contact length, you need to square root RD. R is the radius and D is the draft. Then draft will be obtained from here, not from here. He didn't give me this one, so you maximum draft, then you get this one L, then you apply force, then you get the force value based on that. So this is idea. Right. Okay, so I think this is the time. Time is just finished. I have to stop class here. Let me stop recording.